Welcome to part one of Demystifying DoDAF. And we're going to talk about our most fundamental question, which is, what is an architecture? Well, of course, there's all kinds of architectures. Most people think about architecture as building a house. And if you're used to doing that and having ever built a house, you understand the difficulties associated with that and why you get an architect. And recognize that most of the people you're going to talk to are going to think that's what you're talking about when you're talking about architecture. Of course, there's all kinds of other types of architectures we're going to be talking about. Information architecture, data architectures, technical architectures. These are all different kinds of architectures, or different ways to describe parts of an architecture. Information architecture is all about the information and how it flows through your systems. The data architecture is the more detailed schemas that you might develop in an architecture. Technical architecture is about standards. In fact, there was a joint technical architecture in the Department of Defense for quite some time, which was the JTA, and that was just a listing of the standards that were used. Software architecture, of course, is all about the software, how it works, often described in a modeling language like Unified Modeling Language, UML. For us old-time systems engineers, we always thought about logical and physical architectures because that's a breakout of the functionality and the physicality, and we separate those two to have a better way to work on developing the system solutions. Of course, there's on the right-hand side of that column, there's lots more architectures, types of architectures. It seems like every other day somebody's inventing a new type of architecture. So I like to think about architecture as being one of the most overloaded words in the English language today if it's not abused. So what is an architecture? What's a good definition for an architecture? That's what we're missing. So let's talk about that. Let's look at some popular books that have definitions of architecture. First one is a book by Melissa Cook. She talks about the architecture being the basis for business control over contractors. Well, I like to tell the government folks that that's a joke. You know, you can't control contractors. We're uncontrollable. So that's okay. But actually, that's a really good book, particularly if you're interested in the Zachman framework. It has a lot of information that's associated with that. We're going to talk about Zachman again in a minute. Another book is by Mark Mayer, and that's a terrific book. In it, he uses this definition, which is the structure in terms of components, connections, and constraints of a product, process, or element. That starts getting into some of the dimensionality of the problem, but doesn't give us a whole lot of that, unfortunately. What that book, though, is really good in is the rules of thumb, heuristics of doing good architecting. So it's the art side of it, and it's a powerful book for that reason. Another good book is by my friend Dennis Beatty. He has this definition talks about it as three separate architectures: functional, physical, and operational. That's a breakout very similar to the early days of the C4ISR architecture framework, which was the predecessor to the DoDAF. So, but if you look at all those definitions, are those practical? Well, not really. I think we came up with a little bit what we think is a little more practical definition, which is it's a fundamental and unifying structure defined in terms of elements, information, interfaces, processes, constraints, and behaviors. And behaviors is one of the most important parts of that. We want to make sure that the behavior is something we understand and control. Why? Because the worst thing that can happen to a warfighter is to have a situation where a behavior is unexpected. Even if it's a good behavior, it can get you killed. Okay, so since our job is primarily to keep our warfighters from getting killed, then let's make sure we track behavior. Well, of course, what are the implications of that? The implications include the fact that you need a number of dimensions to describe it, not just technical dimensions, but programmatic dimensions as well. And so those are captured as part of that idea. Also, an architecture needs to form the foundation for a dynamic analysis. Now, why dynamic? Well, these things are time dependent. Behavior particularly, but even the elements themselves change over time. And so we have to have the ability to do that. Unfortunately, most of the approaches people take, and even most of the DoDAF views, are very static in their orientation. And so you have to add that time dimension yourself. So what we need to think about is what are the dimensions that we need to capture in the architecture to make sure that we understand what the information is, we can describe it correctly, and again, for the purpose of specifying things to be done and developed over time. So what are some of the dimensions of an architecture? First of all, the operational context is very key. We have to understand the threats, the environment, all the things that are part of the context that the architecture is going to work within. Then, of course, we're interested in the missions. What are the missions that need to be accomplished, and so we can focus on those. We also need to understand the requirements. Those include laws and policies that have an effect on accomplishing the mission and making it work. Of course, relationship between the requirements. Oftentimes people forget that requirements just stand by themselves. They need have the relationships between them captured so we understand when requirements change what the impacts are. So relationships are going to be very important. That also establishes the English context for things, and so that's an important factor. Organizations and roles to operate within the context and to accomplish the mission, those are very critical. We need to understand those. We're trying to not just architect systems, but we're architecting people, and so that becomes an important factor, an important dimension. Relationships among the organizations, of course, as well. Again, I mentioned relationships for requirements. Relationships between organizations is obviously a critical factor. Behaviors and functions. Those are important to understand. We just talked about behaviors, and we want to understand what those are, and of course, again, the relationships between those functions. Data and information, of course, from the analyses has to be captured and be understood and linked together with these other factors. So again, these relationships between those are important. And of course, constraints on the design are important to capture as well and understand. Now clearly, an architecture becomes the highest level of design, and so all the other design work follows from the architecture. And one of the biggest problems, though, people have is they forget to capture the assumptions. We make all kinds of assumptions and trade-off studies in our heads all the time. We don't capture them, we don't document them. So further downstream, when somebody's trying to understand why was something done, they don't have any rationale for it. So that's another part of capturing and creating ultimately a decision database for this information. So what does an architecture look like? Well, to some people, it's a collection of diagrams and documents. For example, a PowerPoint presentation is the pretty picture. That's the OV1 you'll be hearing about in part 2. That's the cartoon. Everybody loves it. It's got to have the requisite number of lightning bolts and icons and things moving around. We actually do a nice job with that, where we actually animate those as well, so it makes it kind of more interesting and actually tells more of a story. Of course, other kinds of diagrams, the line kind of diagrams with flow charts and nodal diagrams, we're showing things tied together and how they're linked together physically. So those are important type of diagram. And then we have hierarchical diagrams, recognizing that these things are decomposable, and so in fact you have those kind of diagrams as well. And of course, the last set of diagrams I have for you are tables. Tables and matrices give you all kinds of ways to capture information and relate it and show how people understand things. And of course, last but not least, they always show up in a document. And that's great, and those are helpful, but the problem with documents are you can't change them easily. Now, that's maybe the good news and the bad news of a document. But the problem with then a lot of documents is they become what we call shelfware. They sit on a shelf or become a doorstop, and that's it. They're ignored, they're forgotten about, they get dusty, and no longer can be fixed. When things change, and change is the normal factor in anything we're developing in DoD or anywhere else, then we need to be prepared to deal with that. So how can we deal with that in a better way? Well, the way I like to look at it is as a decision database. If you capture all this information in a repository, and then use that repository to create these documents and diagrams, then that's a very much more powerful way to be able to induce change and deal with change and still keep configuration management of your design. So that's very important. So now that we understand what an architecture looks like, what do architectures do for us? We need to understand how that factor works in. So one of the things they do for us is they help us understand the as-is. We want to capture that and understand it so we can work with where the gaps are. We can find the gaps and the problems associated with it, and so those are the things to be fixed. These can be procedural. These don't have to be just systems. So think broader when you're thinking about the as-is. Then, of course, ultimately, people have a vision. Where do they want to go? What do they want it to do? What do they want to do different? How can we apply new technologies and new solutions to solve bigger problems? How about problems that maybe we haven't anticipated before that we want to start thinking about that are taking us out of the box? That's what the vision's supposed to do. Now this gives us our two goalposts, right? We have where we are and where we want to be. Now, how do we get there? Well, that's the transitional architecture. So recognize that you may have multiple transitional architectures over time. Now, one of the problems with this is a lot of people say, well, what's the hardest one of these to do? Well, some people think it's the 2B because they don't have the vision. Some people think it's the as-is because that's a moving target. I like to think the transitional architecture is the most difficult because it has to do with the money. And if you're dealing in DoD, you're always talking about the budget cycle and the money and how that goes. And a lot of what you're developing these architectures for is to help you justify the budget and what you're going to be doing in the future. So recognize that you may need a number of these to help you stair step to where you really want to go. You may not be able to get there all at once, but the transitional architectures will help you get there. That's a very powerful way of looking at it. Now, clearly what this does is give us then the ability to understand the past, the present, and the future. And that helps us a lot in what we can do with architectures. Of course, now the next question would be, who uses an architecture? Well, let's get into that. Well, here's an example from Zachman. I mentioned Zachman a little bit earlier. He had a great way of putting together the users there on the left-hand column. And if you look at the top, is the top-level interrogative questions they might ask. Now, if you look at what those are, they're the 5WH model, which is used in the journalism world, has forever, you know. And so those are very high-level questions and bins for it. But that doesn't really help us so much in understanding how it's going to be evaluated. So let's take a look at another model. This came from one of the earlier versions of the DoDAF, where they have the different potential evaluators. Now, these are the people who are going to use the architecture to make decisions to a great extent, or develop products and solutions. And so if you look at that, it goes from complexity, from the more complex, the more depth, to the more higher level, which has the breadth of impact. So architectures usually are looking at the breadth, but I must be able to develop all the way down. So you're going to be working, in fact, at all these different levels potentially with your architecture. So you have all these different constituencies who all have different roles, different perspectives they're bringing to the problem, and also all kinds of different questions they're bringing to it. So look at these and study these for a second, and I think you can see these are the kinds of problems and things that you want to deal with and be prepared for. So, having looked at that, how does architecture, you notice I mentioned system engineering several times. How does architecture relate to systems engineering? Well, let's talk about that. First of all, what's a system? That's always a confusion to people. From DoDAF 2.0, they have a definition of a system. A system is now defined in general sense of an assemblage of components, machine, human, that perform activities. Since they're subtypes of performer, that's part of their schema, is the performer class of schema, and are interacting interdependent. And that's a very interesting definition of a system. you could use that same definition for system of systems. You can use that same definition almost for architecture, couldn't you? So it's an interesting thing. So we like to look at it a little more broadly. We like to look at it as people, things, and processes. So that gets us into a much broader set of things, and that's what historically we've dealt with in system engineering. So let's look at some of the principles of system engineering that are associated with that. Well, first of all, one of the things we do in system engineering is define the requirements clearly so that they're succinct, people understand what they are, and also they're verifiable. And that's something that is part of that clarity. We want to establish and understand the linkage. How are they tied together? Remember we talked earlier about requirements needing to understand those relationship between requirements. Well, that's part of that linkage, and also the decomposition. In fact, we want to enforce the accountability. That's a critical factor. Accountability is important. Understanding ties back to the roles and responsibilities. We also decompose iteratively. So now we get more and more depth as we decompose, but that linkage, those relationships have to still be there, and you can't lose those in that decomposition. We also have to employ meaningful measurements, and meaningful measurements are metrics, which are measurements not just for the sake of measuring, it's also to make a decision. And so you don't just measure everything, you're trying to capture the real metrics of the system. So that's what we're establishing. Same thing with standards. We want to make sure we use the proper standards that are appropriate to us and to what we need in the process. That gives us consistency. It keeps the design flowing and allows more interoperability if we use standards correctly. Another thing we're trying for is optimization. We're not trying to be perfect with this. You got to remember, better is the enemy of good enough. We absolutely need that optimization instead. And clearly, I mentioned relationships again between the components. That's also another part of that whole tying together and linking things. Now, we have to apply all these with rigor, discipline, and consistency, or we're not going to be effective in what we're doing. So bottom line is the goal is to optimize the relationship amongst cost, schedule, and performance. Those three factors have to be balanced. Too often we get the cost and schedule fixed on us, and so all that we can vary is performance. That's a problem, okay? Particularly in early stages of architecture, we have that analysis of alternatives and time to look at alternative approaches that can deal with the cost and schedule as well as the performance factor. So recognizing that'll help you do a much better job of applying it at the architecture. So let's talk about the architecture and systems engineering and how is it that it's part of it. Well, clearly, architecture and system engineering constitutes the key initial phase of the system engineering process. Again, we're looking at the system engineering much broader, perhaps, than some people do. A lot of people look at it as a narrow niche that gets you to system design. We look at that breadth. So this is just a key initial phase. It's clearly our highest level of system design, as I mentioned before. It employs the system context. So now we understand how this system fits within the bigger picture, or the system of systems. It clearly documents the relationships among requirements, and that's critical to the system design. That's one of the big products architecture is trying to develop, is the requirements so that system designers can do their detailed design work. Similarly, the behavior to implement the requirements is part of that, so that gets us also to one of our other key products in system engineering, which is processes and procedures. It's not just a matter of the things you're going to design hardware and software-wise. This is also the things that can be used for training and operations and support. Has to be developed iteratively and should be maintained and updated as the system engineering phases progress. So again, that tells you that there's going to be change. You're going to have to keep track of that change. This is, again, why the decision database is a key resource and a key need. It also results in the principal description of a system, and of course, it provides a key foundation for analysis and verification for the evolving product. So again, the requirements that you're developing here in architecture are going to have a huge impact in buying off the system in operational test and evaluation. And of course, it provides that key support for that final validation that this is something that's workable, something that's usable in the field, and so now the operators can have something they can rely on. Well, I've kind of hinted at this, so let's talk about the next thing, which is the life cycle. So one of the things to look at the life cycle is, first of all, that you're starting always from a current state of operations to support. There are no green fields. We're always dealing with legacy systems and legacy situations. And we also have to recognize that these are going to be disposed of at some point, that you're going to have to get rid of them. And people think that that's easy. Well, of course, the nuclear industry found that out in the 50s, how difficult it is to get rid of nuclear waste. Well, we have equivalent problems with software and systems all the time. There's hazardous components now in many of the systems, so those disposal issues become paramount. So this cradle to grave is part of what we're looking at the life cycle. So our developments have to be in those contexts of where we're going from beginning to end. And so some of the other stages are, of course, architecture development, system design, hardware software acquisition, integration and test, operational test and evaluation, and transition. And notice during those phases we don't put things in like training. That's obviously a key part of it. So your processes and procedures are part of that as well. So all that gets tied into these different steps. And then finally, we are ready for a future state of operations and support. So now that's a good way of looking at the different major steps in the life cycle. If we look at that, there's a decomposition that goes on in that first phase where you're breaking it down into elements that we can go buy or build. By looking at it this way, it's called a waterfall model. It starts and it's very sequential. And this is a very standard way of looking at the process. We find that this is not the best way to look at it. We prefer a different approach. And what we do with that is we reorganize these steps into something that looks a little bit more like a V. And it's called the V model. We're still doing the decomposition coming down the V. But on the upside, we're coming back and integrating it. And so we're integrating the pieces, so we actually abstract back up to the bigger system that actually works, that we can test it in the full operational environment. We like this model because it reminds us we're doing things as we come down the V that are critical going back up the V. We're creating the operational test and evaluation requirements as we're doing architecture development. We're also creating the operations support environment. So again, you can even start some of your training aspects and some of your processes and procedures right at the very beginning of the process in architecture. That makes it very powerful. So again, recognize also that this happens in a context of program management all the way through. So the programmatic side of this problem has to be dealt with as well. That's part of that cost, schedule, performance we're optimizing. So here's another approach, and some people call this a life cycle model. This starts with requirements analysis, which is understanding what the requirements are, decomposing them. It's a functional analysis and allocation is the next step in this process, and synthesis is the third. Those are the three primary steps of this model. And again, some people call this a life cycle model. It's not really quite that. It's more of a process model. It also has another activity that goes on in parallel with those three major steps, which is systems analysis and control. This is where your trade-offs live and those kind of activities that control how we change and how we adjust those different steps. Now, if you notice the lines between these different types, a lot of people read this as a waterfall diagram. I start with requirements analysis and I go to functional analysis and synthesis. Well, that's really the classical system engineering textbook approach. Well, the reality of it, things are, particularly in the architecture world, is we rarely start with a detailed requirements document. Oftentimes we get a very high level statement of need, and that's all we're working with. We're sometimes even lucky to get that. Of course, what we often have to do is look at what's out there and reverse engineer it and take a look at our as-is architecture that way. And so from that, we then understand the functionality of how things work, and then from that we can derive the requirements that are associated with it. Another approach I like to, particularly for the 2B architecture, where I don't have requirements and I'm not really sure I want to be tied to today's systems too much, I try to work in the middle, which is functional analysis and allocation. This is a powerful place to do it, and one of the keys to that is scenario analysis. We create scenarios the operators understand, and then from that we can abstract up to requirements level to get the big picture, and then we can decompose down into the system design levels and things like that. So it's a very powerful approach, which I'll talk about in part 3 a bit more. Well, here's another view of that same diagram, and if you notice, there's an oval, and that input at the top and output at the bottom doesn't tell you where you need to start. So that fits well with the previous diagram, and this gives you a little more detail. You can find this online. It's available from the EIA standard. It was originally in the draft MIL Standard 499BE document. And so that's out there and available for people if you're interested in more details. So let's take a look at the full life cycle processes. We like to actually take that process diagram, which we previously used, and reapply it at each of the steps in decomposition. So sure enough, that ends up being simpler approach to dealing with the life cycle, because now I'm using the same basic process all the way through, just at different levels of decomposition. By doing that, we've reduced the training costs and the difficulty of learning that. So what did we learn today? I hope you got as a key summary out of this that architecture is a key part of the initial systems engineering life cycle. It employs the principles of systems engineering if you want to be effective at doing architecture, and it gives you your highest level of design. Clearly, you need to use a practiced methodology to do this, and you want to develop it iteratively, working with your users and your customers and developers, and working as a team. And then clearly want to use it throughout the life cycle of the system. For some further reading on this, again, I reference these books that I talked about a little bit earlier. They're all very powerful. There's also other great texts and available things. There is a book on the DoD architecture framework, which I wrote back some time ago. We are updating that book in the process, and we're pretty excited to have that entry in the fall this year.